Hello! Today I'm going to be telling you about an emerging field of technology known as nanorobotics and some of their applications in the future. Just around 30 years ago, robots used to be an imagination of both Hollywood and science fiction.
I'll be back.
Now, they have become an integral part of our world of manufacturing technology. We have created robots that are highly functional and intelligent, adapting to the world around them. Thanks to computing technology, some are even smarter than us. We have created robots that are very realistic, and some that are very entertaining.
This is good football! Tucks it in!
But what does the future have in store for robotics? Most areas of science are converging to a newer, much smaller area of study known as nanotechnology, working with atomic and molecular building blocks that range from 1 to 100 nanometers. A nanorobot is a robot that can precisely move, function, and sense at this small scale, and has applications in the world of biomedicine and beyond. So just how small is a nanometer, you might ask? Since I'm a fan of tennis, we'll start with a tennis ball, which is about 100 million nanometers, or 1/10 of a meter long. Zooming in, we have a large grain of sand, which is 1 million nanometers long, or 1 millimeter. 10 times smaller than that is the average diameter of a human hair, which is 100 microns, or 100,000 nanometers. 10 times smaller than that, and we're at the size of a cancer cell. A bacteria, a virus, an antibody, and finally a glucose molecule, the size of a nanometer. Now that you understand how small a nanometer is, the next question you probably have is, how can you build robots this small? One such manufacturing process is a method known as two-photon polymerization, in which a focused ion beam etches geometry into a substrate that is deposited with nanoparticles. It is then built up layer by layer, and then the initial substrate is etched away. You are left with a high-precision, small-tolerance device that can be used in a nanoroboot. These nanorobots could potentially act as a drug delivery system, reducing the need for insulin shots for diabetics, and potentially targeting cancer cells and destroying them. They could also be used to remove plaque from artery walls or attack other infections such as pathogens in the bloodstream. In addition, they could be used in cells to repair DNA by removing damaged fragments. In the brain, they could act as a neuron repair agent to prevent the need for certain brain surgery and cure certain psychological disorders. A final future application of biomedical nanorobots would be an artificial red blood cell known as a respirocyte, a 1-micron oxygen vessel powered by a glucose engine that provides 236 times more oxygen per unit volume than a red blood cell does. Just 1 cubic centimeter of a 50% saline suspension of respirocytes can replace the gas-carrying capacity of a patient's entire 5.4-liter blood. Victims of heart attacks can survive for 4 hours with 1 liter of respirocyte suspension, which would save many lives. This vessel can support up to 3 billion atoms of both carbon dioxide and oxygen, making the robotic respirocyte more efficient than a biological red blood cell. The potential for nanorobotics for biomedical applications is just about endless. This all sounds pretty exciting, but how close are we to nanorobotics becoming a reality? Researchers at Rice University have developed a single-molecule car through chemical self-assembly that features carbon-60 buckyball wheels. It is about 3 to 4 nanometers long, which is about the width of a single strand of DNA. When placed on a gold surface and heated to about 200 degrees Celsius, the wheels begin to rotate about their alkyne axle attached by a carbon-carbon single bond. Its position is detected through a process known as scanning tunneling microscopy. Future nanocars can have molecular motors or pumps attached to them for automated drug delivery. Zooming out to the micro world, 1,000 times larger, Professor Bradley Nelson of the Institute of Robotics and Intelligent Systems has developed a 200-micron magnetic robot that can perform intraocular microrobotic surgery on eyes to treat ophthalmic diseases. This Sumerian cobalt device is inserted through injection, which reduces risk of infection or bleeding that traditional surgery has. This micro-robot is controlled by an elaborate system of electromagnets which can move the device in any direction or rotate it about any plane. It is extremely resistant to high temperatures and demagnetization and features a drug delivering capability through an equipped micro-syringe. In addition, Bradley Nelson has developed a biomimicry flagella-powered magnetic robot that can move up to 5 microns per second at 470 RPM. Although this video shows linear motion, this can be attached to larger objects to rotate them. He hopes to scale down these robots to the nano world to function like the nanorobotics you saw earlier. Researchers at Carnegie Mellon University are studying a very different application for smart nano-electromechanical systems in a field that they refer to as claytronics, or programmable matter. The idea of claytronics is to manufacture sub-millimeter computers that can move about one another and reassemble into various shapes, sizes, and colors depending on what the user inputs. Each computer, which they call a cadom or claytronic atom, must have the capability to communicate with nearby cadoms and attach and detach a mechanical bond to function as a system. Some of the major challenges claytronics faces is scaling down the size of cadoms and keeping their function in a three-dimensional system, which is a challenge of both material scientists, mechanical engineers, electrical engineers, and computer scientists. A very early 2D macrocadom features a series of 24 electromagnets to prove the concept. Using computer simulation for 3D cadom moving algorithms, researchers can provide animations of cadom system assembly and disassembly for formation of shape in claytronic systems. This powerful technology has application in hands-on rapid prototyping, having multifunctional items that can change shape to one's customization, and redefining the world of communication with a very realistic and physical representation of social interaction. I hope you enjoyed this video and are now more interested in the emerging fields of nanorobotics, nanomedicine, and nanotechnology.